you. I wanted to make sure that everyone knew my email address. I talk to people all over the world all the time, so if you want to talk to me, that's the way to get me, because even when I'm here, largely you haven't seen me a lot around, but that's because I'm on email actually taking care of business like other places. So if you really want to reach me, as I said, I can always be reached, as many, many people can testify no matter where I am. I have computer accounts, in fact, all over the world, too. Okay, so with that contact information out of the way, we want to resume our discussion from yesterday. I'm going to make some slight changes because yesterday's discussion, I wasn't really being extremely careful at every point. There are factors of i's and maybe some 2's or what have you. Today we want to be a little bit more precise. So I ended yesterday's lecture by pointing out an analogy between something that Robert had been working out for you in his discussion of group theory, namely that a transformation is an idea of something that acts on something else. That's what a transformation is. And this idea of acting, however, when we start writing on paper, can take the same idea can take many, many different forms. So, for example, as I sat through Robert's discussion of O2, he wrote down for you the matrix that implements the transformation, calling it A. And yes, it does exactly what he said it did. But then in my lecture yesterday, I gave you another way to look at A, that it's not a matrix at all. In fact, what we saw yesterday was if I multiply this thing here by an appropriate number and exponentiate that, it does exactly the same thing on X and Y as the matrix does. And so, therefore, it is another representation of the same idea. That's what representations are. They're ways of writing ideas. And so then I pointed out that, well, I actually needed this because one of you actually pushed me very far afield of my planned lecture, and in order to answer the question, I had to talk about Lorentz transformations. So we sort of got to this stage and stopped yesterday. I wanted to continue a little bit along those lines because we're going to need some of these ideas a little bit later. And in fact, these dovetail very beautifully with some of the discussions that have gone on previously, principally in Robert's lectures on group theory. Okay, so in Robert's lecture, if you look at the subcase D equal 2 for O2, you'll find out that the thing he wrote down as an invariant takes exactly this form. It's the sum of the squares of two coordinates that were the things that the vectors act on. This particular object doesn't change under the effect of an O2 rotation. And, of course, that's something we all know because, okay, here's a stick. And the O2 rotation means turn something around an action. So that means I become the exponential of t. So here I've done my job. I'm the exponential of t. I've turned the stick. And now if you came along with a tape measure and measured the stick first when it was this way, you would get whatever its length was. I'd turn it like this. You'd come back with your tape measure, measure its length. You'd get the same number. And that's why we call things like this invariants, because their numerical values are not changed by the action of turning. Okay? Now, it turns out that, as I said, I needed this thing over here because someone was asking me all sort of horrible questions. And so I eventually argued for you that in a world that has 4 dimensions, there are 6 of these things, and that again dovetails with Robert's discussion that for O6 there should be 3. The way you count the number of rotations is you count the number of pairs of planes and then divide by 2 because you've double counted. So for the case of D equal 4, there should be 6 rotational-like objects. You'll notice that instead of writing SO4 here, SO4 in this location, I wrote in yesterday's class or lecture SO13. And now there's a significance of what. Now 1 plus 3 surely equals 4. But it's significant that I wrote the 1 separately from the 3. And the notion, of course, is that in our world, we have 1 temporal dimension and 3 spatial dimensions. So I'm looking at the set of transformations that act on Minkowski space. And so here's a representation of a vector in Minkowski space. Here are the partial derivatives of that same vector. And this object must be some kind of rotation. I exponentiate this, multiply by some number, and it does the turning but now on these four-dimensional objects. What's the invariant associated with this? Because yesterday I didn't get a chance to write the invariant. It turns out that the invariant associated with these transformations is this object. Something well known for people who study relativity. Namely, in relativity, you know that no matter what Lorentz frame you're in, the numerical value of this thing, which is sometimes called the invariant length or the invariant time, depending on who's talking about it. Well, in this form, it's called the invariant length. If I divide by c squared, you could call it an invariant time. But the point is that this thing is just like the length of a stick, but in this four-dimensional world that Einstein teaches us is the basis for actually it was Minkowski who teaches us is a way to understand what Einstein discovered with special relativity. Okay, so that's sort of where we were yesterday. One other thing I wanted to point out to you is that when you calculate the change, that's supposed to be a vector, so I'll put some arrows here. When you calculate the change in the vector, the way we always calculate the infinitesimal change of something is by taking the generator, and again, we saw this in Robert's lectures. We act on the object that we're trying to perform the change on, and then we multiply by a parameter that tells us how close to the identity we are. In fact, if this parameter is 0, it means we didn't do anything to the object. So the way we typically write transformations, and these are called transformations that are homotopic to the identity. That's a fancy way of saying that these transformations can be smoothly mapped into the identity. And again, an example of that is if I take my stick, well, here I am, you go out of the room for 5 minutes, and you come back and you see me doing this again, and then I ask you, well, gee, was there a change at all? Any sort of change? Even in orientation, you say, no change. So I was the identity map, right? So doing nothing is the identity map. And so therefore, if I did nothing, there was really no change in this. Well, that means you would want the change in it to be 0, but that occurs when I set the parameter equals 0. So the parameter measures how far away from the identity map you are. And mathematically, we say such transformations are homotopic to the identity map. It means it can smoothly be joined to the identity map. Okay. So going back yesterday and now being a little bit more precise, we were talking about what these supersymmetry changes had to do. We're going to write them today in the form of they're going to be something that induces a change, so that's how we use our delta symbol. But today we're going to come back and realize that there has to be this parameter that measures how close we are to the identity. Now, I introduced it yesterday. I didn't say very much about it, but here it is again. So it's the epsilon. And in order to make this transformation look as much like an ordinary rotation as possible, I throw in a factor of I. Now, the I doesn't do anything fundamental, but it just tries to make the comparison between rotations and supersymmetry as close as possible. Now, the other thing, but yesterday, of course, you'll remember that when I wrote the analogs of these two equations, I said the thing that sits over here has to be a fermion. So if you compare what I wrote yesterday to what I have here today, then it must be the case that this object, whatever this thing is, it must be the thing that turns a boson into a fermion. Otherwise, this would then be inconsistent with what I wrote yesterday. So Q, the supersymmetry charge, is an abstract idea, it's an abstract thing, whose effect on bosons is to turn them into fermions. And the effect of Q on fermions must be to turn them into bosons. Otherwise, what I wrote today is not consistent with what I wrote yesterday. Now, the other statement I made yesterday was what happens when you perform two of these kinds of transformations successively and then take the opposite order. So we could perform one of these transformations with now, depending on epsilon, because now we know epsilon is sort of the angular variable for supersymmetry. We can have also done that with a different value angle, a different angular, quote unquote, because these aren't really angles, but they're like angles, so we might as well refer to them that way, value. And then this is supposed to be compared with what happens if you do the transformations in the opposite order. And my statement was, it's supersymmetry if. And the if was that what we should get on the other side is a translation, but it depends on the parameter A in some way, which we have to determine. And this should be true on all bosons and fermions. This statement should be mathematically true. Let's write this out in a little bit more detail. The delta symbols, because we now know that deltas are always this combination of things. That's how you implement the delta. So I can write this as minus I times epsilon alpha q alpha. That's that thing. And then minus I delta eta alpha q alpha. That's that thing. And now I'm going to observe that what's really sitting here is a commutator. I'm getting lazy. I don't want to write it twice. So I'll simply put my comma in the middle. That means do it twice with a minus sign in the middle and close the bracket. And then on the other side, I will explicitly realize the fact that the way that I implement translations is this. So I have, where's it? Minus I, I'm sorry, is that an I times A, PA? So we get this. Let's straighten this up a little bit. The two factors of I here, I can get rid of those. Putting a plus sign there, so there's nothing mysterious about that. And now, this isn't quite what I wrote yesterday, because in order to get exactly what I wrote yesterday, it must be the case that the parameter A that sits here has got to be equal to epsilon alpha times eta beta times a symbol I wrote yesterday as gamma alpha, mu alpha beta. And I don't remember anyone asking me what that symbol was. Oh, you did? Okay. Did I explain it? No. I didn't think so. So we need to come back and talk about what is this thing. Now, in some sense, you know in a general way what this is, because again, if you follow the logic from Robert's lectures on group theory, you recognize that this thing is almost like a structure constant. It plays the role of the structure constant. It tells you how to recombine the two symmetries when you put them on the other side. Now, we say almost like because it's different in one. This set of relationships is different in one very fundamental way. This thing here is really the derivative. And so we have to worry a little bit, but this plays the role of the structure constant. We can just settle that for the moment. Now, what is this thing? As I have now been properly challenged, we have to go a little bit afield and talk about the history of the development of quantum field theory. Let me begin by observing the following. Let me make a definition. This is some matrix. Now, how big is this matrix? Well, let me not specify that for the moment. We'll come back later and talk about alpha and beta run from 1 to some value, some finite value. We don't want it to be an infinitely big matrix, but some finite size matrix. And this matrix, we want to put one requirement on it. Well, first of all, there must be 4 of them if we're in a 4-dimensional world, because the number of these matrices is exactly the number of translations. So if we were in a world with 4 coordinates, there must be 4 of these matrices. If we're in a world with 26 coordinates, as you might have heard about at some recent time, then we need 26 of these matrices. So this is controlled by looking at how many independent directions there are. Yes, sir?
Sorry, just to be clear, your alpha beta matrix indices and your mu's are Lorentz.
My mu is a naming label. That's the way to, yeah, because it tells me which one of these matrices I'm talking about.
But it varies from the dimensions in space.
Yes.
So
It turns out to be the Lorentz vector index, yes.
So what are you using to raise your indices, the matrix indices?
Oh, God, you guys are good. One of your astute colleagues observed that I wrote this structure constant here with both of these indices down. But when I came over here, I wrote them with these indices one up and one down. And if you should be very careful. This is a very telling fact. When you start working with tensor notations, you should be very careful on the altitude of the indices, whether it's upstairs and on the roof or whether it's in the basement, matters. And so the question that was just asked me, well, since you claim that this is a structure constant, what is its relationship at all to this object? And I have to give you that relationship, or this is ill-defined. The relationship is as following. Let me introduce something that's often called the Spinor Metric. It's an object that I'm going to specify has the following properties. It's going to be antisymmetrical, first of all, if you were to interchange the two rows with columns in it. Also, in my conventions, and you don't have to do this, but because a lot of people choose to do it different ways, but I like to choose these matrices, these metrics, so that they are always purely imaginary. They must be n by n matrices because they have to. The range of their indices must be the same as the range over there. And then the final property I will use to specify these things is that these things are invertible. So there exists an object C beta gamma, which is the inverse of this, in such a way that this equation is satisfied. So there's a Spinor metric. And now, using this Spinor metric, whatever this thing is, I can relate it back to that by the Spinor metric. Now, Spinor metric is not, like I said, it's not something that you find in a whole lot of the math and the physical, even the physical literature, but these things exist. You can show that in any case where you can construct gamma matrices, there are Spinor metrics. And so now, to answer the question that was put to me, I say that gamma, mu, alpha, beta is really a shorthand notation for C beta gamma, but let me call it delta, times this structure constant thing, alpha delta. Yes, sir.
So this Spinor metric is a strange kind of object. For one, is that it's antisymmetric, right?
Yeah.
Normally, we're taught to think of metrics as rank 2 symmetric objects. Interpret told us how we could interpret that geometrically as telling us how to measure distance.
That's right.
Is there any such interpretation for the Spinor metric?
Nope. Ultimately, we're going to find out that there's a fundamental reason we want to choose this thing to be antisymmetrical. And when we try to measure lengths in the space where this thing is a metric, it will turn out we don't want any definitions of length. If you let me put that on pause, we'll come back and talk about this point. So now we have a really interesting mathematical structure. It's very precise. We've got all our coefficients set and everything. And now let me do one other piece of business. I want this equation to be true for all possible choices of epsilon and eta. This equation should not be valid just for one particular choice of epsilon. It should be valid for all choices of epsilon and eta. So what I'm tempted to do in that case is to perform the following. Let me write the commutator now explicitly out one more time. I'm sorry, I should have called this a beta index. Equals to I excuse me just a moment. Yes, I'm okay. I times epsilon alpha eta gamma mu. Alpha beta times p mu. I'm sorry. I'm worried about a factor of I, but let me proceed, and I'll come back perhaps and change it. So I have this equation, and now I'm going to do something. We're going to switch gears entirely. I'm going to ask you to solve a little problem for me. What's the solution to this equation? Right? X has got to be plus or minus 1. No big deal. What's the solution to that equation? Plus or minus I. What's the solution to this equation? Sure about that? Someone's been reading ahead. Let me point out something very interesting about this sequence of things here. At some point in your life, when you were still probably in grade school, or perhaps low levels in middle school, you knew how to manipulate numbers very well. You could add and subtract them. You had learned about the counting numbers. You had learned about zero, the negative numbers, fractions, and then ultimately even irrational numbers like pi or e. All of that was in your arsenal of understanding of what the idea of a number was. Now, I want you to try to go back in your mind to that time. Okay? So you're, I don't know, maybe in grade level. I don't know how the system here compares to the U.S. Typically in the U.S., you were probably around grade level 7 or maybe 8 when someone challenges you with this problem. Now, at that time, remember, we know the counting numbers, we know the reals, we know zero, we know the irrationals, right? But no one has ever told you that there's anything else called a number. And so if you actually go to schools, and you can try this experiment, go get the appropriate age child who's pretty good at mathematics, and say, solve this problem. They won't be able to solve it. And the reason they won't be able to solve it is because no one has introduced to them the notion that there's another kind of number that's beyond the numbers that they've already seen. Because you have to have the idea that you can have another kind of number. And in fact, I always thought it was highly amusing that we call these imaginary numbers, since all numbers are imaginary. They're all things in our ideas, so they're all imaginary. So to call this an imaginary number is really ultimately it's kind of an abusive language. But the point is, someone had to come along and tell you, oh, you're free to do something else. Right? So now, with this experience in mind, I want to come forward in time today and again challenge you to solve this equation. Now, most of you rapidly blurted out the solution is x equals 0. Yeah, that is a solution, but it's not the only solution if you will expand your horizon about the meaning of numbers. Let me talk about numbers for a little while. The reals we know very well. They're sort of in the world around us. They start with the counting numbers. They go through the fractions to ultimately the irrational numbers. Those are kinds of, the irrationals we have to struggle a little bit because you learn how to take limits, or you learn to measure the radius of a circle relative to the circumference. So those numbers sort of come out of the world around us. That's why they're really kind of fixed in nature. We see them all the time. But that equation, x squared equals minus 1, in order to solve it, we had to go outside the concept of those numbers. And so we invent a new kind of number that we call the complex numbers. And it starts here, we can say a number is algebraically represented by A. But here, when I start talking about numbers, I can represent it as A plus IB. I have to use this fundamental thing, A, the I, which is the new number I invented. Now, it turns out this is not the end of the number systems that mathematicians have actually figured out. After this comes a set of numbers called the Quaternions. And what Quaternions are, well, they're a kind of number where you have 3 independent i's. So if you were to write a Quaternion, let me use the symbol Q, it would be of the form IB plus J C plus KD, where A, B, C, and D are all reals. A, B, C, D are reals. That's just like in complex numbers where A and B were reals, right? So that's nothing different there, saying the coefficients are reals. But in front of the coefficients, there's something that's like the likes of which you've never seen before. It's a new kind of number. Now, the way the quaternions work is that the square of I is equal to the square of j is equal to the square of k, and they're all equal to minus 1. That's why I said it's like you introduce 3 copies of the unit I. But in order to have an algebra, you must know how to multiply, for example, I times j. And the rule is that I times j is equal k. J times k is equal I, and k times I is equal j. Well, that's all very well and good. Well, almost. What about how to multiply j times I? I'm sorry. I times j is k2. I times j is k. You're asking what is k times I? This is the key question. If I reverse the order of these things, what do I get? For quaternions, the answer is minus. So this is actually minus j times I. This is equal minus k times j. And this is equal minus I times k. So quaternions say that when the order of the symbol matters when you perform the multiplication. But once you are willing to accept all of this, then these things are kind of a generalization of complex numbers. Well, it doesn't stop there. There are worse things in the mathematical world. There are a set of things called octonions. And they're kind of like you have 7 copies of I. So an octonion looks like a real number plus 7 other real numbers. And we're going to use tensor notation to simplify ourselves. So we're going to write this as in this form where I goes from 1 to 7. So we're rapidly inventing numbers all along. And then it even turns out that this is not the last number system known. There's something called Cayley numbers. And if you want to know how many basis elements are going on here, you should note there's an interesting pattern. Here we just needed one object to talk about the real numbers, one fundamental object, actually the number 1. And the other numbers, that number times 1. Here we actually need 2 fundamental objects, 1 and I. Here we need 4 fundamental objects, 1, I, j, and k. Here, there were 8 fundamental objects, 1 and ei. And so what might you guess would be the Cayley numbers? 16. And that's right. So a Cayley number is something that is written as a real number plus 15 other real numbers times a basis element that I'll simply call, call it F. And here I goes from 1 to 15. Now, you might imagine, since I'm inventing all these numbers, and I'm not going to specify the multiplication tables of these things. It takes us too far afield of where I would like to go, but they're well known to people who study mathematics. You might say, well, since you're inventing these numbers, why don't you keep going? It turns out you can't. There are no more number systems of this type of generalization after the Cayley numbers. They stop. It's a deep fact of number theory. So if you want to know why, you've got to go study number theory. But it's true, they stop. I've never seen it. Never seen it. Maybe there, I've just never seen it. But it stops. The system stops at Cayley numbers. Now, there are other things that are really interesting about this pattern. That is, every time you do this, turns out you lose some property of numbers that you're used to. For example, With the reals, since the reals are all ordered along the real line, the notion of greater than, less than, or equal to makes perfect sense. Because you can ask where are the points that represent these relative to each other on the real line. So 2 points can either be one to the left, they can be 2 points at the same, or the first number could be to the right. Those are the only things that can happen. So greater than, less than, or equal to, ordering, is well defined for the real numbers. What about for complex numbers? Is ordering well defined there? The answer turns out to be no. If you have two complex numbers, there is no intrinsic way to say that one complex number is greater than the other. You lose ordering when you go to the complex number system. Now, complex numbers do have sort of a modulus, and you can say the moduluses are moduli are ordered, but the complex numbers themselves are not orderable. So you lose that property here. But all the other properties of numbers, you have. In particular, you still have commutativity. Two complex numbers, z1 and z2, is equal to z2 times z1. So you still have commutativity at this stage. When you come to the Quaternions, you lose commutativity. And that's implicit because we started getting into this business about the order of the multiplication of these symbols. So you lose commutativity with Quaternions. When you get to octonions, you lose something else. You lose what's called associativity. And it's exactly associativity in the sense that Robert's been talking about in his lectures, about the composition of things here. You lose the associative property of the triple product of three numbers. And now finally, you get to the Cayley numbers. And at the Cayley number, what you lose is the numbers no longer form what's called a division ring. Well, what's a division ring? Well, a division ring, the simplest way to think of a division ring is if I have a Cayley number, some Cayley number, K1, and I write this as another Cayley number times K2, the product of two other Cayley numbers, K2 and K3. This equation in general cannot be solved with Cayley numbers. It can be solved with Quaternions. It can be solved with complex numbers. This is the definition of a division ring. Cayley numbers don't form a division ring. And after you go down all the properties we have lost in this, there's essentially nothing else that we do formally with numbers. And in that sense, maybe that's the best intuitive proof. But I've never thought about that as any kind of a proof. But that's what happens with these are called the classical number fields. Okay, so I did all of that to try to get you used to the idea that you can make up numbers whenever you feel like it.
So what property do Cayley numbers do?
Oh, God, I don't remember. I'd have to go to the library and look it up. So the question is why, what good are they exactly? I don't know. I don't remember right offhand. Okay, so you should, from this experience, if you haven't seen these things before, you should take away from this that numbers you can make up, you can pull them out of a hat just like a rabbit. Yes, sir?
I just want to know, it's clear that these numbers have certain algebraic structures. Isn't the algebraic structure the most important thing and not necessarily the numbers?
Yes, in fact, that's what's going on here. So we're changing the algebraic structures. And after Cayley numbers, I don't know that... See, the point is that when you change the algebraic structure, there is still some logical consistency that you must require in the system. And it turns out that that you can find these logically consistent manipulation rules for all of these things, even in the last case when you lose the division ring property. So yes, it's actually the algebraic structures that are the important questions at work here.
We don't necessarily have to use these numbers.
Ah, exactly my point. Someone is racing ahead of our thought processes. Since here, what's really the important issue is what are the algebraic properties of the things that you manipulate, then you suddenly realize that you have freedom. So I come back once more time. To my challenge here and say, what's the solution to this? Well, now we have freedom. We have liberated ourselves emotionally and mentally from the notion that we know all the numbers that there are. And in particular, we can introduce what's called a Grassman number, introduced in the mid to late 1800s by the mathematician Grassman. That's why we call them Grassman numbers. Mr. Grassman said, I want to solve this equation, and it has a non-zero solution. He introduced an object that those of us in supersymmetry often call theta. It's a kind of a quantity. It's a number. And its defining property is that its square is equal to 0. It plays the same role that I does with the complex numbers. There, the defining property of I is that they square to -1. So the defining property of a Grassman number is that its square is 0. I'm now going to go back to the equation here and do something sort of terrible. That I is really bothering me.
So there are 3 solutions to that equation.
Say again?
So there are 3 solutions to that equation.
Well, theta is the solution to this equation, yes. 0 and Grassman number. Yes, all of those are solutions. Or actually, there's an infinite, because I can do a real number times theta. That's still a solution too. Right? 6 theta is still a solution. 17 theta is the solution. Pi theta is still a solution. Right? All those are now solutions. So it's not like there are just 3 solutions. There are lots of them. I'm sorry? Thank you. I was wondering, I kept wondering why I was upset about this I. In my last lecture, there was no I there. Thank you very much. So go back and remove it from today's lecture. Okay, so now I'm going to do something violent. So you should hold on to your seats. I am going to assert that these things are all Grassman in nature. That they have a Grassman property about them. That means that, for example, this thing here, this D index was running over some range, but each one of these objects squares to 0. So we're going to say these things are actually Grassman numbers. So we identify eta and beta are Grassman. Well, you can think of them as, let me put it this way, call them vectors of Grassman numbers. Because they're collections of Grassman numbers, independent collections of Grassman numbers. Now, we also, well, if we have lots of these things, then we have to worry about how they move past each other. So if I have 2 Grassman numbers, theta 1 and theta 2, how do they act when I move one past the other? And it is consistent if you have 2 of these things. If you have theta 1, theta 2, it is consistent to say that this is equal to minus theta 2, theta 1. So they anti-commute, just like the Quaternions did. By definition, if you introduce multiple copies of Grassman numbers, they anti-commute with each other. Okay? Now, this is actually very important because it's going to change fundamentally the commutator that sits here. The Q's themselves are not numbers. Let me make that clear, because the Q's are the effect on the fields. So those themselves are not numbers. And we will declare that you can move Grassman numbers past the Q's. And if we do that, we then find that what's left over looks as follows. It reads epsilon alpha eta beta times q alpha q beta minus eta beta epsilon alpha q beta q alpha is equal to epsilon alpha eta beta times gamma mu alpha beta times p. We want to write this equation in a way that's explicitly independent of epsilon and eta. So in some sense, we want to, well, it turns out you can't divide by Grassman numbers either. But we want to write this equation in a way that's independent. Now, there's a problem with that because the order of these 2 terms is different from the order of the other 2 terms in the equation. And if they're Grassman numbers, we've declared previously that when we see products of Grassman numbers, they intrinsically anti-commute. That means that this equation can be written as this. I'm sorry? Epsilon alpha, eta, beta. Right? And now I see that there is a common factor on both sides, and it's certainly true that this thing here, if it's equal to what sits behind the second Grassman on the other side, satisfies this equation. And so what we get is something rather remarkable. Namely, yes, ma'am. I can assert linear independence of these things, and that's sufficient. So I'm not saying, I don't have to actually divide by it. If these things are linear independent, this equation must be satisfied. Okay, so you get this. And what's remarkable about this is that now we have left Robert's discussion. Because in Robert's discussion, every single generator that you talked about had an algebra which was formed by using commutators. This is an anti-commutator. And this is the origin of why Q charges anti-commute to the translation. They don't commute to the translation. So in that sense, they're not like groups. And in fact, so this is an anti-commutator. Anti-commutator. And this is what's, well, let me finish the rest of the discussion. Yesterday, I also wrote relationships for Q and P with P. So let me go and pull those out. If you look very carefully, it is consistent for this to be true. And I don't know who pushed me into anti-de Sitter space today, but I'm not going to let you do it today. So we write this. Yes, ma'am. No, we declare that gamma is just an ordinary set of numbers. They can be real or complex. We restrict them to the reals or the complex. I've never seen a construction. In fact, that's an interesting problem, whether you could let this thing take values over any of the other fields. I've never seen any generalizations like that. The only known generalizations use only real or complex values for this. Yeah. But remember, that's because these things are formally like vectors of Grassman numbers. These two are commutators. Now, yes, sir. Yes, sir.
Remember I said Grassman numbers, they don't form a division ring.
I didn't say that, but that's actually true. Grassman numbers don't form a division ring. But I didn't say that, but that's right. Well, no. What you did is actually heard two different statements from me. I defined what a Grassman ring was, and then I said you couldn't divide by theta. So you concluded that thetas don't form a division ring. And that's right.
So in that statement, it comes from exactly that.
Yes.
Come to that, but divided both sides.
That's not true. What I've used is, because there's another way to argue, and that is to use the linear independence. You see, these things are like the different directions in a vector space. So if someone said, I have an equation where a vector times something is equal to something else times that vector, and it's supposed to be true for all vectors, because I point out to you, you can't divide by vectors either, right? And you constantly, if I wrote the matrix equation, M times V is equal N times V, right? And I would ask you, what's the solution? What would you tell me? But did you divide by V to get that? So whatever you did there, if you're happy with that, I want you to do that up there. Okay, so this structure here in the box is what we call the supersymmetry algebra. And it's the basis of supersymmetry. We want to find things that represent this property. Now, remember how it works. When you say that you have an algebra, well, first of all, you have to have the things that do the action, but they act on objects. They act on other things. So in the case of matrices, the matrices are the things that do the turning, but they act on vectors, which are the things being turned. Right? So these things, our challenge will be to find the objects that these things act upon. That's one of our challenge. And then make sure that the relationships work out so that this set of things is true. So let's go over here. So that's the supersymmetry algebra. Yes? It's exactly analogous. It's exactly the same problem. If I start with the standard model and say I have some group SU5, then I've got to find things that realize that group. I have to find 5-plets and 15-plets, and then I have to find the matrices that act on them, because it's those matrices that are actually the representations of SU5, of the SU5 generators. So it's exactly the same problem. Yes, and in fact, this is very important. What's going on here is you have a kind of charge. I didn't actually unify Lorentz. It's translations here that's being unified. But still, it's the unification of a space-time symmetry with something that's not a space-time symmetry. And this is one of the unique features of supersymmetry. And in fact, for a very long time, people thought this was impossible. There's a very famous mathematical physics result called the Komen-Mandula theorem. And Komen-Mandula theorem says it is impossible to join together space-time symmetries with what we call internal symmetries. So how come I'm able to do it here? Answer turns out to be one of the assumptions of Komen-Mandula theorem is that you only use commutators.
So now translations are not that great. You use this method as well?
Say again?
Now you just have translation of invariance there. Or like,
Well, if you follow our colleagues' league who likes anti-de Sitter space, then in fact I would be unifying the Lorentz generators, the translations, and these Qs. In that case, yes, all of them are unified. Okay, so now we have our challenge. Let's see if we can meet it. We want to find objects that realize these ideas. So they have to be objects that these things act upon in such a way that this abstract set of relationships is satisfied. That's the goal. Let's see, how much time do I have? 20 minutes. Great. Okay. $10. 25? Okay. In order to try to reach our goal, I'm going to point out some things that you already know. So we're going to start with this statement. Most famous equation in all of physics. Even lay people on the street. In fact, there's a book that's written about this, about something called the history of the equation or something. Most famous equation in the world. Einstein gives it to us. There's another equation that you physicist types know. It comes from Schrodinger. Says that at least the way Mr. Schrodinger likes to do physics, E is in fact I h bar d by dt. So let's go ahead and combine these two things. Because Mr. Schrodinger also says you have to introduce things called wave functions. So if we combine these two relationships, E equals mc squared and E goes to I times ht, we are then led to the following equation. Now, this equation is a first-order differential equation, and so even a professor should be able to solve it. And in fact, the solution, which you will not be surprised to know, is simply that this thing that I call psi can be written as some constant of normalization. Let me introduce a quantity b here. In a moment, it will be obvious why I want to do this. And then times an exponential of minus I m naught c squared over h bar times t. Sure enough, it's got to be the solution. Just do the derivative. Now, you'll notice I introduced this strange little factor here. And the reason is because I want to declare that psi is an anti-commuting function. Psi of t is an anti-commuting function. So you can have as soon as you introduce anti-commuting numbers, then any ordinary function times an anti-commuting number is an anti-commuting function. And that's the role of B. Now, if you look at this equation, and if you know some relativistic quantum field theory, you say, wait a minute, that looks suspiciously like the Dirac equation. Let me subtract this from this side and put a 0 here. Sure looks like the Dirac equation to me. Now, one thing about that equation that I just wrote, let me pull it down, so there it is. If you do physics long enough, let me say it this way. That is a version of Newton's second law. Because what it does, what Newton's second law tells you is how things move if there are no forces acting on them. And this is sort of an equation that tells me how this thing behaves. And it turns out there is sort of a force here, but let me act like it wasn't. Let me just call this Newton's law. If I call this Newton's law, then one challenge I could face is, can I get Newton's law from the calculus of variations? Now, in ordinary physics, the answer is yes. Let's remember how the calculus of variations works. Calculus of variations, for an ordinary example, let's write ordinary Newton's law, would say the mass times the derivative, the second derivative of position with respect to time is equal to 0. Or in fact, I could even put a force here if you wish. So let's go ahead and do that. Make it a conservative force, because I like conservative forces. So here is Newton's second law in the presence of a conservative force. Is there something that we can use, the calculus of variation, that leads to this? The answer is yes. It's called the Lagrangian. So calculus, and here I'm assuming that you've seen the calculus of variations. You can talk to me separately if you have not. We can talk about it. But if we write L is equal to a half of m dx dt square minus v, using the calculus of variations, we get this equation. So, is there something that we can use to get that equation by the calculus of variation, by the standard methods of calculus of variations? The answer turns out to be yes, there is. What I must write, well, let's see. Let me do this slowly. I might be tempted to write this. And if you know the calculus of variations, you know why I would be tempted to do so. Because essentially the way the calculus of variations says, I can treat psi and psi star as independent variables, and then differentiate this thing with respect to psi star, and demand that that derivative equals 0, and then pops that equation right back at me. So it's very tempting, therefore, to identify this thing here as the object that plays the role of the Lagrangian. Now, there's only one problem with this identification. Lagrangians are supposed to be real functions. But Mr. Schrodinger tells us we like psi's to be complex. And in fact, it better be complex because there's an I right there in that equation. And so for a real function, this equation makes no sense whatsoever. So psi is complex, still, as usual, complex. And therefore, this thing is not real. And therefore, we have to work a little bit to find a real Lagrangian whose variation gives us the equation that we want. Now, I had prepared, since I'm short in time, I had prepared a long discussion about what this object is. I'm going to simply give it to you. And again, if you're really interested in details, I can do that offline. It turns out the correct answer, so this is, I'll call this L guess, because it's actually the wrong guess, but it was a good guess. The correct answer turns out to be equal to I times I times h bar with a factor of a half times psi star times ddt of psi minus ddt star psi times psi close minus m0 c squared psi star psi. That's the correct thing. This is a real function, and when you that's what we need for Lagrangian. And when you do the calculus of variations, use your standard calculus of variation rules, you can prove that this gives the equation, the equation of motion there. Okay. Now, one thing about our declaration, because remember we declared that this thing is an anticommutative number. Melanie, you don't look happy. Am I doing something wrong?
No, I'm just checking the factors.
Thank you for checking. So here's the thing that acts as a Lagrangian whose calculus of variation gives the right equation of motion. No. No, there really isn't. There's an integration by parts. There's a secret integration by parts at work here. Okay, so there's our Lagrangian. And now, my colleague, Professor Becker, has been teaching you guys about the string. Now, it turns out that I'm going to borrow a result from her. I'm going to say, let me introduce a complex real function. I'll call it x. I think that's what you called it. Oh, I'm sorry. I didn't mean real, just a complex function. I meant a single complex function. So Dr. Becker in her lectures has been talking about, although she has lots of extra indices, what I'm doing is as if I'm taking Dr. Becker's lecture and I'm declaring that I'm interested for some bizarre reason in looking at the string, but only where the motion is, only where the string depends only on the time direction and not at all on the sigma direction. And I declare, furthermore, that I don't really care about any transverse directions. I only want the x0, what's going on with x0. And I've complexified it for reasons you'll see later. So, from Dr. Becker's lecture, at least the complex version of it, I would be led to look at this as a Lagrangian for something. Now, there are many different ways I can motivate this. I can tell you I'm looking at the two-dimensional harmonic oscillator, but rewritten in terms of complex variables, because I can take x plus iy, x minus iy, and then if I take the sum of the two oscillator equations, they join together nicely, and they're the same thing as this. So one way to say this, I'm looking at two oscillators, two harmonic oscillators. H bar squared plays the role of the mass, and this combination M naught C squared plays the role of K. So that's a system that you know a lot about, so you should be pretty comfortable with that. And now, I can derive the equations of motion for this if you wish for me to. They turn out to be nothing but minus h bar squared ddt. Again, I'm using calculus of variations to do this. Minus m naught c squared times x is equals 0. I'm sorry? This B? I'm sorry, this B? Because I want to make sure that I'm not talking about this Lagrangian. So I have to name them differently. Yeah. No, it's a naming label, so I know which Lagrangian I'm talking about. Okay, now, I am going to give you an exercise. First, but let me motivate the exercise first. And I'm going to do this by going back to Robert's lecture on O2. For O2, I have told you guys a couple of different times now. Let's see, X, this has got to be a Y, it's an X. For O2, for a couple of different times now, we've said this thing acts like the generator of the O2 symmetry. And if you have the variable X, you calculate its change, its variation, by taking, for that case, minus I times alpha, where here alpha is the angle of the rotation, times t, and then you take t and you let it act on X. That's what we said variations are for O2 symmetries, right? So everybody's happy with that? Everyone, that's well defined. Okay, now, I will give you a problem. And this will be the last of our exercises for the day. The problem I'm going to give you is the following. Let me define, and again, this is a naming label. Let me define Lx to simply be x to the fourth power. Okay? What is the change? Let's actually call this O2. What's the change in this? What's the change? Well, I'll say it several different ways I can ask it. What's the change, or does it change at all? It's sort of the same question. Does this thing change under the action of the O2? Well, the way that you answer that question is you do the calculation. So what does the calculation say we have to do? Well, we have to take the very... I keep inserting these I's where I don't need them. There's no I there. Okay, so the variation in L2, in Lx, you calculate by taking the generator, the parameter times the generator, and then you put Lx to the fourth behind it. That's what it means to calculate the change. And now, can you do that calculation? I sure hope so, or else you shouldn't be in this room, right? This is equal to, well, t itself, I'm sorry, I do need this I, but what I don't need, let me try this one more time here. I do need the I here, but what I really want to do is write this as this times x dy minus y ddx. And now I've gotten rid of all the i's that keep confusing me so much. This is the same I that's been bedeviling me all day. Right? So the change in Lx is this. Now, can you do that calculation? Well, yeah, right? I mean, because these are derivatives. This is some function. Do you know how to differentiate? Yeah, we all know how to differentiate. The answer is, well, if you have something to the fourth power, you first get that thing to one power lower. This alpha comes along for the ride, so it's still out there. And then you have to take this derivative thing and then act on x itself, right? That's how you should perform this operation. Now, when you do that derivative, this acts on that to give 0, but this acts and gives something. It's not 0, right? Because it's derivative x acting on x. And so what we're left with is minus 4 alpha x cubed times y to the first power, and that y is coming from here. So the quantity Lx is not invariant under this variation, the O2 variation. Now, suppose someone came along and told you, but I want you to use the x to the 4 function for some measurement or some reason, but I'm going to allow you to add on to it in such a way to get an invariant. And the things you add on can depend on both x and y. Right? So so we're going to modify. We're going to form an Lx hat, and Lx hat is going to be the Lx that we started from, And then you are allowed to add extra terms that depend on both x and y. So what terms do you pick? And the guiding rule is, however you add them, we want the net result to be invariant, not to change. So you say, well, let's see, I can start adding x's and y's. Well, I could put a constant here times y if I wanted to. I can put another constant here times, a different constant times x. So those are some extra guesses. Or I could put here a third constant times x times y. And boy, this game goes on a long time. But let me point out a special class of terms. I could also, ultimately in this game, put some constant here with a term that reads x cubed times y to the first. And in this long list of things, let me call this a1 plus a2. There's another term here which is x squared y squared. And then there's an a3 times x first y cubed. And then there's finally a term a4 times y to the fourth. And of course, you could keep playing the game forever. You could keep adding more and more and more polynomials if you wanted to. No one could stop you. But we want to demand that the O2 variation of Lx hat should be equal to 0. That's our demand. We want to have something that involves x to the fourth, but we want, after the extension, we want this thing to be invariant under O2. It turns out that that requirement is so strong that it fixes all of these constants. And in fact, the solution to this equation is that Lx hat is equal to x squared plus y squared squared. And you can now, of course, read off all these constants, or these particular a's that I've picked out. For example, the x3 y to the first, this turns out to be a 3. I'm sorry, 4. No, 2, sorry. Because you have to square this up and see what it is. Oops, I'm sorry. It's a 0. Sorry, it's a 0. So this is a 0. That's a 0. That's not 0 because it's the cross term that comes out of here, and that turns out to be a 2. This turns out to be a 1. And so if I want to use this x to the 4 function, and I want something, so I'm looking for a function that contains x to the 4th, but it must be invariant under the O2, then this is the function that I must use. So we see how symmetry kind of works here. If there's something that you want, and you have a symmetry, and you demand that the thing you want must be part of a bigger object that has no change, then you have to add extra stuff to it. That's how symmetries work. And you could do this for you could raise x, you can find lots of other examples to see how this goes. And so now, I am going to, here I have LF. Let me write under it LB, just one more time, h bar squared dd x, the first power dx by dt minus m 0 c squared x times x bar. So there's LF and LB. Let me assert and give you as an exercise. Suppose someone came along and told you that I had done a piece of science, and I know that the world is controlled by this object in my imaginary world. I've done an experiment. My experiment is totally consistent with this thing describing the physics I have measured. So that's step number 1. I must have physics described by this. Step number 2, someone else comes along and says, well, actually, your world has supersymmetry in it. And therefore, there must be something that is invariant under the supersymmetry, because that's what symmetry, when you say it's invariant, means it doesn't change. There's something that's invariant under the supersymmetry, and yet must contain the piece that you know describes the physics in our that you've measured and postulated by this first function. So let me tell you that there's an invariant that I can form by taking the sum of these two things. Now, you shouldn't accept that I got it right because you see me made lots of errors here at the board today. So how do you prove if I'm right or wrong? Well, what you must do... Oh, my goodness. What you must do is write a set of variations. So I'm going to write some variations for you. I'm going to say the variation in x is going to be equal to some complex Grassman quantity times psi with some ordinary number here. Let me call that k1. The variation in psi is going to be equal to that complex number barred times ddt of a with some choice of number here plus a quantity I'm going to call, a new quantity I'll call f. Oh, that's horrible. So let me introduce something for you. F times f bar. Let me call this f, a little f. A little f. And now finally, delta q of f is equal to epsilon bar times some number. Call this one 3, call this one 4, times d by dt of psi. So I'm giving you an exercise. Can you find these four constants, k1, 2, 3, and 4, such that the variation on LB plus LF plus L little f should be equal to 0? Can you find constants that do that? If you can find constants that do that, we have proven that that is an invariant. Now, I'm going to tell you the answer is yes. You should be able to find those constants, but it's up to you to find them. And the next step that we have to do, we don't know that this is supersymmetry yet. All we know so far is that this is a symmetry. Because when you find the variation of something equals 0, it means you found a symmetry. But is it supersymmetry? The way we can show that this is supersymmetry is that up there I have given you a specification. In fact, let me write this in a very explicit form. Call that, because it's q depending on the angle like variable. This is delta q depending on the angle like variable. And this is delta q depending on the angular type variable. D bar? Oh, epsilon. I'm sorry. Just a second. Yes, it has to be. It has to be Grassman in nature also, and it also needs to be here. I'm sorry. Is there an A? This is an A. Yes. Oh, I'm sorry. Thanks, Robert. It's an X, right? So my claim is it's an exercise for you to go and see if you can find the constants such that this thing equals 0. If you can find those constants, the next exercise I want you to perform is to calculate delta q eta minus delta q eta times delta q epsilon. Calculate this on any field in question, either on the x, the psi, or the f, because the variation's over there. So this is a calculation you should be able to do. So these are your homework exercises. And when you do this calculation, I want you to come back and tell me, is this supersymmetry or not? Because if it's supersymmetry, it's got to look like this. That's it.